So I'm going to start off in optics talking about linear polarization. It might seem a little strange to some instructors to kind of jump right to that. I like it because the math is pretty easy. Just a second. It's pretty fun. It's pretty cool. And so that's why I want to start there. It's actually a wave optics phenomenon. So without further ado, let's just get to it. And let me start by reminding you of what an electromagnetic wave looks like with a screen share. Screen one, here we go. So on the screen, hopefully you can see this electromagnetic wave. These blue arrows represent the magnetic field. Sometimes I call it the B field. You could talk to some other instructor about H and things like that. Let's not. And the yellow arrows are called the electric field. And this is a traveling sinusoidal wave. So when I click on the screen, we should see it oscillating. The pink and the purple arrows are just there to kind of help you see one arrow staying in place, just so you can kind of track it. We see the electric field oscillates up and down. We would call this a vertically polarized light wave. This is vertically polarized because the electric field oscillates up and down. All right, so that's our first clue about polarization. And maybe there's other types of polarization where the electric field starts swirling around. That's circular polarization. That's actually common, for example, in the light that leaves an atom. It can have angular momentum, which is associated with its polarization. We can discuss that more some other lifetime. Now, for now, let me get this out of here. I'm gonna turn the screen off so I get less glare. All right, so let's talk about linear polarization. And the first thing we saw is it's related to the direction of the electric field. So when we say something is vertically polarized, now I can't write in yellow on this board, so beware of the blue here, does not represent magnetic field. We sometimes will see this in textbooks as the letter V for vertically polarized light. What do I mean by linear polarization? I mean in a line, as opposed to some light can be circularly polarized where the electric field keeps oscillating and rotating. That's not what we're talking about. We're only going to start with linear polarization. So if something is vertically polarized, you might see it as V. I'll oftentimes just draw it as an arrow up and down like this. Okay, take a guess what this is. You're right. Horizontally polarized light. Okay. You could have it at some arbitrary angle. It doesn't have to be straight up and down or left and right. It could be at some arbitrary angle theta. Now this example down here, notice there's arrows kind of going in every direction. I'm not going to draw every single arrow in the unit, but this is not circularly polarized where it's swirling around. This is my notation for unpolarized light, meaning the electric field. I'll show you in just a second. So in this case, when you have light from a light bulb, some of the light could be polarized this way and that way and this way because it's all kind of random. And so we say it's unpolarized light, meaning the light doesn't have any net polarization. It's randomly polarized. Every single light ray coming out of the bulb does have some polarization, but on average, there's no common theme there. They're all over the place. And now let me show you an example real quick. Let me show you what this looks like with a demo. All right. So hopefully you can see this. And let me hit the lights a little bit so you can see better. I think I want all of them but one. Like that. Okay, so you can see this. This is just a light bulb here. And what I did is I stuck this piece of cardboard on there to kind of collimate the light. It just keeps the light from spraying out all over the room. Nothing fancy, it's just a cardboard tube. Let me make sure that's pointed at the camera again. All right, and you can see here, well, maybe if I turn this light off, you'll get better. I don't know if you can see this very well on the screen. I'm trying to look at the camera at the same time. This is a polarizer. Now, I put pieces of tape on here to mark out different angles, so you may not be able to see them right now. Maybe if I turn the light on really quick, you can see that. So again, there's pieces of tape here, all around here, just so I can get the angles really quick. That's for me. So if you're wondering how I'm going to get the angles at various angles, that's what I'm doing. Nothing fancy. Let me turn this back off here and show you what happens. So what I want to do, I'm going to turn on this light bulb, point it at the screen. And okay, that's there. I'm going to take this polarizer and put it in front of there. And I'm going to set it up so that it's vertically polarized. Oh, I can't see I need to put the tape towards me so I can see. There we go. So this is oriented vertically polarized. There's a big green piece of tape here that maybe you can see. So I am vertically polarized. And what happens here is watch the brightness of the bulb. We see there it's pretty bright. Now, one of the things that's happening is the monitor that I use actually auto adjusts the light level. So you may see the light levels change a few seconds after I put this in front, but just look at the light and then boom, it gets dimmer. And then obviously we see the camera that I'm using auto adjust the light levels right after that. But we do see a brightness dip. All right. Now what happens if I put another polarizer in here? I'm going to use the same orientation. And notice we don't notice that dip, or at least not as much of one. Okay, polarizers aren't perfect, but if we line up multiple polarizers in the same orientation, I can even stick in a third one here. Again, vertically. And again, I'm using my pieces of tape to align these. It's not perfect. We see that the amount of light through 3 polarizers, which are all vertical, is approximately the same as if I just use one, right? But we do see a significant change in the brightness when I remove the polarizer. You see it get brighter, and then the camera is auto-adjusting. Sorry about that. So now what happens here, right now I have passed, and so to be clear, this light bulb by itself is unpolarized. The polarization directions of each light ray coming out of that light bulb is random. So now what happens, how do you get a polarized light source? Well, here's one way. Now what happens is the light goes through this polarizer, and the polarizer has long molecules. You can kind of think of it like a picket fence, and it only allows through light rays which are predominantly vertically polarized. And we'll talk more about the rules in just a second. It does let through some of the light that's near horizontal, but just very tiny amount. Whereas the light that's near vertically polarized, again, with the electric fields nearly vertical, it lets almost all of it through. Okay, and I'll give you the rule on that in a minute. So now what I want to see, if I put in a second polarizer, this one's kind of cool. If I rotate this, you should see the light bulb start to dim. It's getting dimmer, it's getting dimmer. And look at this, almost completely dark, right? So there is still a light bulb there, and that's because no polarizers are perfect. But we say that the transmission, the amount of light transmitted through these polarizers, it's basically nearly extinguished the light, or it's, we say there's a high extinction coefficient. But we don't need to know those terms that well. But now if I keep rotating it the same direction, the light comes back. And now we see it's pretty much just as bright as if that second polarizer wasn't there, because the polarization is matched. Keep rotating again. Gets dimmer, gets dimmer. We see it extinguish again right about there. And so if I keep spinning this, you'll notice that approximately every 90 degrees, it gets extinguished. And then approximately every 90 degrees, it gets bright again, et cetera, et cetera. All right, and you could even stick third polarizer in there, and we'll do that in a minute. Let's go back to the board. I'm going to turn the lights on real quick. Get all of the lights on. All right. Maybe I'll bring a couple of these over here. And almost there. Here we go. Just for fun, I'll show you this again. Here's my face. You can see that my face is about half as bright. And now what happens, if I line up this polarizer the same direction, you can see there's not a huge difference in the light brightness. There's a little bit because there's a little bit of what's called neutral density filter, but watch as I turn this. You don't see my face at all, right? Isn't that kind of fun? All right. So the rules that I want to use to talk about this are on the board. Let's get this video over with. The 1/2 rule. All right. If you have unpolarized light and it heads through a polarizer, it doesn't matter what angle you use. We saw this. We would call this intensity here I0. Make sure that shows up. The initial intensity of the unpolarized light is I0. We call this I1 after the intensity after, I'll call that I1 is equal to 1/2 of I0. Why do I use the subscript 1? Well, imagine if we start stacking up polarizers. I1 could be after the first polarizer, I2 could be after the second polarizer, etc., etc. So it's just kind of convenient to say the light that's incident upon the first polarizer has subscript 0, and then you use 1, 2, 3 for each polarizer thereafter. Let's say we had polarized light. Okay. Incident on a polarizer. And there's angle theta, and there's angle theta between this polarization and the polarizer's direction. Again, you can think of these long lines kind of like the picket fence or the long molecules of in the polarizer, right? So the electric field, if it's up and down here, some of it might get through. If it's perfectly horizontal, almost none of it gets through, right? The equation for this is I0 is incident. Again, here's my first polarizer. We'll call this I1. And we'll say the amount that gets through is modeled very accurately by I0 cosine squared of theta. If there's only one parameter there. So this is called Malice's law. And I'm just going to call this the 1/2 rule. I don't know if it really has a name. But so here's the main rules we're going to use for analyzing polarizers, and that's it. Again, just making clear, it doesn't matter what angle you use here, you always get 1/2. And notice something else. For both of these cases, after the light gets transmitted here, the polarization angle of the light wave that gets through matches the polarizer, not what it was initially. So it was unpolarized initially. Afterwards, the polarization angle matches the polarizer's angle. Okay, let's leave it at that and get to some practice problems in the next video.